All right, we're on section 2 now, discussing radioactivity. And this is all, like I say, a precursor till we actually start talking about the neutron, but this is good information. The first thing it says under section 2.1 is the stability of nuclei. How stable is the nucleus of an atom? And it says, first sentence, as the mass number becomes larger, the ratio of neutrons to protons in the nucleus becomes larger. Non-stable nuclei may have an excess or a deficiency of neutrons. So that's in that ZXA notation number, with the ZXA notation we were talking about. As I start introducing neutrons, more or less of them, to certain elements and changing the isotopic number, I start maybe changing the characteristics of that element a little bit. And once they get away from what is known as a ground state, look what it says, they can undergo a process known as beta decay, or they could do an alpha decay, or a neutron decay, or they could actually just give up energy in the terms of a gamma and try and get towards a ground state. And that was heavily investigated by several late 19th, early 20th century physicists and such. And you can see Becquerel and Marie Curie and her husband Pierre, and they looked at heavy elements. What's key is the last sentence here. All naturally occurring nuclides with atomic numbers greater than 82, I think you might look that up, that's lead, are radioactive. Meaning, when you get lots of protons together, greater than 82, we're going to upset that neutron to proton ratio potentially, and they're now going to become radioactive, and they're going to want to start to decay towards something that's more stable. That's all they're doing, is giving off energy to try and get more stable. So the next thing we talk about is nuclear decay then. And what can happen in nuclear decay? And if you're looking, I'm going to put the next page drawing up. But that ratio of neutrons to protons, and I'm going to put the neutrons down here, and I'm going to put protons here, and then I'm going to put what we call the line of stability. Here's a line of stability. So all atoms, all elements, all isotopes are trying to be on this line because it represents a low energy state, essentially. And it's very predictable if you're up here, what type of decay is going to occur versus what's going to occur here. And the 4 types of decay I previously mentioned were, one was a neutron turning to a proton can turn to a neutron. I could emit what's known as alpha decay, or I could do gamma decay, or even another one called electron capture, which isn't really a decay. So this is kind of cool. We can predict, if based upon where the isotope is relative to this line, what's going to probably happen. So let's say I have an element, an isotope of an element that's right here. Well, obviously, for this number of neutrons, it would like to be here. It's proton heavy. So what would happen if some sort of decay turned one of its protons to a neutron? It would have one less proton, so it would go in that direction, and it would have one more neutron. And look, so if I'm up here, I want to turn a proton to a neutron. If you're looking, excuse me, under the next page, you'll see that turning a proton to a neutron, this right here, this is called beta positive decay. Beta positive. And the way it does it, this is an E right here, by the way, beta positive decay turns a proton to a neutron. Goes one down and one over towards the line of stability. You can probably guess what's going to happen here. If for this number of protons, I didn't have enough neutrons, well, the neutron will turn to a proton. It'll go one over, one less neutron, one more proton, trying to get to the line of stability. We call that beta minus decay. And this is a beta positive. There's a symbol for these. Beta symbol. Looks like that. And it could be, I'm sorry, that's an alpha. Messed up. Beta. And it could be a positive or it could be a negative. Here's the real kicker. It's just an electron that gets emitted from the nucleus. It's just an electron. A beta particle is just an electron emitted from the nucleus. And we're going to go over that in some more detail in a sec. Another type of decay we have, we talked about alpha decay, right? So these are just conversions right here, neutron to proton, proton to neutron conversion, trying to get the isotope towards the line of stability, and it actually changes the isotope, because if I do change the number of protons, which I did in both cases, I no longer have the element that I had before. Very key. What if I was up here? Somewhere up here where I just had way too many protons and neutrons. So it sure would be nice if I could get rid of a bunch at a time. And it can. This is an alpha symbol. Alpha symbol. And an alpha is a particle that's ejected from the nucleus, and it is actually 2 helium-4 with a +2 charge, which means it is a helium nucleus, because 2 protons and 2 neutrons would create a helium nucleus, but if it didn't have its orbital electrons, it would have a +2 charge. That is referred to as an alpha particle. Alpha emitters are usually very, very heavy isotopes, and they'll give off alpha particles to try and get rid of. They will go 2 down and 2 over. They'll have 2 less neutrons and 2 less protons in their nucleus. So they can get rid of a lot of mass quick, trying to establish a position on the line of stability. A gamma is nothing more than a bundle of energy that when a nucleus is in its excited state, it can give off this energy in terms of and trying to establish a ground state. And that's all it is. It has no mass. I still have the same exact element and the same exact isotope of the element as gammas are given off, but the energy that's contained within it is getting lower and lower as the gammas are emitted. And it's trying to establish a ground state. Electron capture. Electron capture, we said this is beta positive probability. This is beta minus probability. This up here is where alphas would be ejected. Electron capture, what if a proton captured an electron from the orbital cloud of electrons, the most inner ring? Well, that proton would become electrically neutral, and it too would turn into a neutron. So electron capture is also up here in this region. Electron capture. If you have too many protons, you could get electron capture, turning a proton to a neutron, which is 1 down and 1 over. Or you could get beta positive decay, which is proton to neutron conversion. And if I'm down here, most likely it would be beta minus decay. Beta minus decay turns a neutron to a proton by going 1 over and 1 up. And if I was really heavy, once again, probability of decay we would be looking at something like an alpha decay, where I get rid of a helium nucleus emitted from the nucleus of the excited isotope. This is very important. A lot of folks don't realize that a beta particle, there's a beta negative, that is nothing more than an electron. But the reason we don't call it an electron is it's not an electron in the orbital shell. It is an electron emitted from the nucleus. I mean, we didn't think about that when we went to high school or college, unless we took a few classes on this stuff. But we know that there are neutrons and protons in the nucleus. Nowhere is there an electron. And we didn't discuss how an electron can get kicked out of this nucleus. I could get a positively charged electron or a negatively charged electron kicked out of the nucleus, and it's still an electron, has the same mass, the same charge as the electron that you're familiar with. It's just, we're going to call it a beta particle because it was born from the nucleus of an atom, okay? Very good. All right. On the bottom of under section 2.5, where it talks about beta decay, this is a very good example of beta decay. Let me let that focus. Right here, this is beta minus decay. And this is something that we're going to encourage inside our reactor. I'm going to start with a neutron, and it's going to be absorbed. Let me use a different color. Our neutron is going to be absorbed by 92 uranium-235. Then it becomes 92 uranium-236. And then it could absorb another neutron and become 92 uranium-237, and so on and so on. And let's say I created 92 uranium-238. It can either be created by multiple neutron absorptions, or 92 uranium-238 represents the largest majority of fuel that I put in the core. It's what we dig up. So if a neutron was to get absorbed into 92 uranium-238, it becomes 92 uranium-239. 92 uranium-239 is a high probability beta minus decay. And if it were to do that, if it were to beta minus decay, I take this 92 uranium-239 and it undergoes beta minus decay. Well, I know that one of these neutrons up here, of this 239 neutrons and protons, one of the 147 neutrons that are sitting up here turns to a proton. So now I have 93 protons and I no longer have uranium. Nope, I have neptunium. But I still have the same number of neutrons and protons. I still have 239 of them. It's just that one of the neutrons has turned to a proton. So up here, the ratio of neutrons to protons has changed. And guess what? This is a big beta emitter too. And if it emits a beta, I get plutonium, because that is 94 239. So we can convert uranium-238 via the absorption of a neutron, and a double beta minus decay can become plutonium-239. That is a very important transformation. We'll find out that we encourage that transformation due to the properties of plutonium-239. And that transformation is simply shown right here, where a neutron is absorbed by a uranium-238 atom. It becomes uranium-239. It ejects an electron through beta decay, and it turns a neutron to a proton. And now you see I have 93. That makes me have now neptunium instead of uranium. Still have the same number of protons and neutrons, so this atomic mass has not changed. Only this right here, the atomic number has changed. Then this is a big beta decay as well. So it'll emit an electron from the nucleus, turning another neutron to a proton. And right here at the end, I've established plutonium-239. I have bred plutonium-239 from uranium-238. And these have highly different characteristics. This one is going to be very usable in our core. This one, not as much. Even though it represents about 95% of our core, this is going to be more useful. Last thing we talk about over here on the right-hand side is ion pairs and specific ionization. An ion pair. If I was to remove one electron from helium, let's say I have two helium-4, and I know that it has 2 electrons if it's electrostatically neutral. If one of those electrons was to leave, there's a free electron out there. This now has a +1 charge, and these are called an ion pair. The atom has become electrostatically positive, and the product of the two, though, the product of a single ionizing event is this and it's an ion pair. So if a gamma had came in and hit that, that's the ionizing event, and the product of that ionizing event, that gamma knocking out that electron from its orbit, gave me a free electron and a positively charged helium nucleus. The two together are called an ion pair. Now, the ability for these to then go on and do something is called their specific ionization. We talk about specific ionization because it is the number of ion pairs produced in a centimeter of travel through matter. And you read that in the first sentence right here. So once the ion pairs are created, what happens? A particle, its charge has the greatest effect on specific ionization. So the particles we'll look at in terms of specific ionization are an alpha, a beta, which is just an electron. I'm sorry, we'll look at a gamma. This is an alpha. We'll look at an alpha, beta, gamma, and we'll look at a neutron. An alpha is a 2 helium-4 nucleus with a +2 charge. A gamma, it can cause one ionizing event, one event. We'll look at how it interacts with matter in a minute. Betas are electrons. They can either have a plus or -1 charge. A neutron has no charge. So charge has a big effect on ionization. And in this case, I really, really, really would not want my body to interact with an alpha, especially if it was to be consumed or internalized somehow, because it has a +2 charge. So we'll be very careful when around the plant, if we know we have a system that is an alpha emitter that contains liquid or some sort of substance that's an alpha emitter, we're going to be especially careful. We're going to be careful on all 4 of them, but alpha emitters, when they're consumed, are bad. Beta emitters, we're going to be very careful with them as well. We're going to provide shielding for gammas, and we're definitely find out that we're going to try and minimize neutron interaction in our body, because neutrons, they love to give off energy to water, and our body is about 80% water.